Okay, hello everybody, and welcome to a brief tutorial in how to solve a triple integral with where the bounds are a cylinder. So we're solving this in cylindrical coordinates. So the first thing that we're going to want to do is we're going to want to set up our example problem, which here we're going to say we're going to take the triple integral of the square root of x squared plus y squared dv. We'll say that our e, it lies inside of a cylinder, where the cylinder is typified by the graph of x squared plus y squared equals 25. And then we'll say that it also lies, we'll say, between planes. So z equals 0 and z equals 2. So before we do anything, the first thing we're going to want to do is we're going to want to define our bounds. So I'll say we'll do something. This will go with green. Yeah, let's go with green. So the first thing we're going to want to say is so this is a cylinder. So in order to find the bounds of our integration, the first thing we're going to do is we're going to want to look at what we're inside of. And this will give us our cylindrical coordinates. So this is how I solve it. I always do my graph last. I know a lot of instructors and people will tell you to do the graph first. I prefer to get the equation out of the way so I can spend the most time possible on constructing a good graph, because the equations themselves aren't that difficult. When you're seeing something like this, if you see anything like that, you're always going to want to know, as soon as you have something with x squared plus y squared equals r squared, or in this case z, which is equal to r squared, you're going to know that your 0 is less than or equal to r is less than or equal to the square root of your z, which in this case would be 5. And you're also going to know that because it's an x squared plus y squared, it's going to be 0 less than or equal to theta less than or equal to 2 pi. That's going to cover your whole circle in terms of your xy plane. Now, the last thing that we have is that our bounds from z are from 0 less than or equal to z less than or equal to 2. And that's how we got all three of our bounds. The next thing we're going to want to do is we're going to switch back to a lighter color, and we're going to say that we now have to translate this into, so we've already translated our bounds into cylindrical coordinates. Now we're going to translate our function into cylindrical coordinates. So 0 to 5, 0 to 2 pi, whoops, and 0 to 2. And so we're going to do the square root of, well, remember actually that x equals r cosine theta and y equals r sine theta. So, barring that, whoops, r cosine theta squared plus r sine theta squared. It's very messy, gosh. R, whoops, sine theta squared. This is equal to 0 to 5, 0 to 2 pi, 0 to 2, square root of r squared cosine squared theta plus r squared sine squared theta. Which means that we get to do a fun thing actually when we come down here. There we go. So it's, say we'll reconvert this to e. So e, because I don't want to keep writing it, e is equal to the square root of, since we have an r squared term in both, we can remove that. R squared cosine squared theta plus sine squared theta, and given the laws of trig identities, we know that a cosine squared theta plus a sine squared theta is always equal to 1, so this becomes the square root of r squared, which means that we are integrating a triple integral of just r dv. You always have to want to go back and add that in. I always forget it. So that's how you set that up. Now we can actually start to solve this integral. So it's going to be Since we're starting off with an r, then when we expand this out, we're going to want to go with an r first. And our r was 0 to 5, so it's 0 to 5 r dr. Then after that, we integrate with respect to the theta and the z. Oh, whoops, actually. Yeah, theta and the z, so yeah. 0 to 2 pi. We'll just do it like that. You can do this in any order. Some orders will be easier than others, obviously. But I'm just going to do it rz theta because I see an r here. Whoops. R squared, that's because we always have our Jacobian constant of the r dr. So since we already had an r, now we get an r dr. So now we can just take this into 3 parts. So we'll be doing this first. Whoops, good lord. We'll be doing this first. Then we'll be doing this. Then we'll be doing this. And a neat trick that my instructor taught me is that when you're integrating with a triple integral, this becomes a constant that is pulled into here and treated as a constant because you're no longer integrating with respect to r, you're integrating with respect to a different variable. So you can actually multiply these out. So this ends up looking like this because think about it, if you integrate from, 0 to 5 r squared dr, you're going to end up getting a number, just a scalar number that you use to integrate your dz, and then you get a scalar number from your dz that you integrate into your 2 pi. So you can end up just doing this, 0 to 2 pi d theta times 0 to 2 dz times 0 to 5 r squared dr. You can only do this when you don't have any equations in your integration bounds. So if I had, say, 0 to 5 plus y, or 0 to 5 plus z, I wouldn't be able to do this. Or I wouldn't be able to do this as easily. And I'm a little lazy, so if it's not easy, I'm not going to do it. Anyways, we'll just take this one at a time, starting with r 0 to 5 r squared dr. So this becomes 1 over 3 r cubed, 0 to 5, which means that we end up with 1 over 3 times 5 cubed, which is just equal, and I always do it all super long like that, but that's your first one. Now on to the second one. It becomes 0 to 2. We can put the 5 cubed over 3 as a constant. We can remove that from the integrand. We just end up with dz, which is equal to z 0 to 2, which is just with your constant here. I'm removing it for the sake of speed, because this part is actually fairly easy. You're just integrating, and we all already know how to integrate if we're doing this kind of problem, hopefully. And so we just end up with 2 times 5 cubed over 3. So that came back over here. Now we solve with respect to our theta, 0 to 2 pi, right? This becomes 2 5 cubed over 3 d theta, which just ends up being theta 0 to 2 pi, which equals 2 pi times 2 times 5 cubed over 3. If you want to solve that, then you're absolutely allowed, but I usually just leave it unsolved because instructors aren't really going to mark down. In my experience, they don't mark down for you having super complex and unsimplified integers. They just want to make, if anything, that actually helps them see where you may have created any errors in your integration. So with this as our final answer, we can actually write out the full thing, which is that let's write it out long form. We won't just use e, we'll use the whole thing. So 0 to 2 pi, 0 to 2, 0 to 5, and I'm messing up the order now because I can. R squared dr, dz d theta, is equal to this thing right here, which is 2 pi 2 5 cubed over 3. And there it is. That's your final answer for the equation. Now, in my experience, a lot of instructors will give you very minimal credit for figuring that out because it didn't take a very long time. The real beast is going all the way back up to the top. Whoops, this is my old math work. The real beast is actually going all the way up to the top and graphing our E right here. That's what we want to look at. So, we'll bring all these bounds down here, and we'll just graph it in, I don't know, maybe red, maybe yellow. Let's do pink again. I liked pink. So, when you're graphing, we have our E bounds, which is a cylinder, x squared plus y squared equals 25. Needs to be within this, and it needs to be contained by the z equals 0 and z equals 2 planes. So, between.
Recording.
I'm recording. I'm going to put it on YouTube so people know how to solve the problem.
Huh.
Yeah, I know, I'm a nerd. So, now you know, it's up for debate. Am I a nerd? Am I a geek? We'll see. But, so let's graph this. We'll put our z-axis here. And your graphs never have to be super accurate. They just have to be recognizable, in my experience. So, that's z. That's y. Whoops. I mean, that's x. These actually, it could be anything you want, but for clarity's sake, I'll use a standard, which is xy plane on the floor and z extended. What I usually do when I graph like this is I actually usually do my z coming towards the viewer, and I do my y here and my x here. I find that it's a little bit more intuitive, and as long as you make sure that your axes line up, it's fine. So, but for the sake of today's, I know a lot of people tend to graph with xy on the floor, so I'll graph with xy on the floor today. X, Y, Z. So we want to be within this x squared plus y squared equals 25 cylinder. So all you have to do is you have to make a circle. You know, it doesn't have to be great. It just has to be there we go, something like that, right? Ooh. There we go. Notice how I haven't drawn any numbers yet. That's because I don't want to draw any numbers until the graph is finished. So now we have our xy, and here's what I'll do. I'll add it in here. We'll say this is 5, and this is 5. And that's our cylinder with a radius, well, that's our circle on the floor with the radius of 5. And since it's a cylinder, it means we also extend to a radius of 5. But wait, we're not extending to a radius of 5 because we're bounded by the z equals 0 and the z equals 2. So instead of being bounded by a radius of 5, we're actually a radius of 2 with respect to our cylinder height, with a height of 2. So we'll say we go here, we've essentially cut into our cylinder and stopped it short, and z equals 2. And at x equals 5, 5 equals y. And there you go. That's how you graph your cylinder. So if we were to extend this out a little bit, I'll show you what I mean. So this is saying that we've now placed a plane here. And this plane is stopping the cylinder from reaching its full potential. And this cylinder is stopping, or this bottom plane at z equals 0 is stopping our cylinder from extending any further below the x-axis. Actually, I don't like how that looked. There we go. So we'll pretend that that's straight and not crooked as heck. But that's how that would look if we were to draw the planes. I don't usually draw planes. I usually just draw my solid being cut short by the plane. And we can infer that a plane is supposed to be there with the extension of this cutting line. And you usually, I know in engineering, we would cut in the direction of we would have arrows pointing in the direction of the cut. But we're not in engineering. We're just in calculus, so this is 0, 0, this is 0 to 5, 0 to 5, 0 to 2. And that's where our bounds came from. So if you did want to graph first, you would see if you were to graph this cylinder without knowing your bounds mathematically, you could graph this whole cylinder and count it out and do little, oh, you know, here's my circle, here's my pi, here's my, you know, all of that stuff, and here's how far up it goes. And then you'd know that is a very bad circle. That's a very bad cylinder. But then you would know. And here's why the only bound that isn't really explicitly explained here is the bound for 2 pi. And that's because when you're taking the angle from here to here, you want this to be the whole angle all the way around. So that way you get the whole cylinder. So, for example, if you wanted to only take the cylinder bounded at, say, in the first octant, so that's 0 to 2 pi, your cylinder actually wouldn't look like this anymore. It would look more like, how best to draw this? There we go. Actually look a lot more like this. So you have it here because you're only sticking in the first octant. And it would be cut. And it wouldn't continue along the back side because it would be a cut cylinder. It would cease to exist at x equals, it would cease to exist along your xz and zy planes because you've cut it at the first octant. And this isn't really a very good, this is why I like to graph in the zy, in the zyx direction instead of the xzy direction, because when you do it in xzy, it looks more like this. So if you have, it looks more like that. And you would see that you're missing the rest of your cylinder. But as it stands, you are stuck kind of in the xzy just by convention, and I may or may not do a video on altering your axes in order to get a better graph. But for now, that's how you solve your integral, which was originally e triple integral square root of x squared plus y squared dv. This is our OG, so to speak. And this is what we end up with. Thank you for watching.